My name is Joseph Rosenstein, and I'm a professor of mathematics at Rutgers, the State University of New Jersey. This is a video of my invited presentation to the Discrete Mathematics Topic Study Group at the 13th International Congress on Mathematics Education, referred to as ICME 13, in Hamburg, Germany, in July 2016. The title of this presentation is The Disappearance of Discrete Mathematics from Primary and Secondary Education in the United States. Greetings to everyone. I appreciate the invitation to speak at this session, and I am sorry that due to my reduced mobility, hopefully temporary, I cannot present my remarks in person. The title of this presentation speaks of the disappearance of discrete mathematics from primary and secondary education in the United States. How has this happened? Discrete mathematics has been pushed out of the curriculum of most public schools because of the focus on creating and implementing curricula based on the recently introduced Common Core standards in mathematics. Every school and district is concerned about the performance of its students on assessments based on this Common Core, and about the consequences for individual teachers and for schools of low performance on these assessments. That is, teachers are being judged on the performance of their students, and schools and districts are being judged on the performance of their students and their teachers, even though both are inappropriate uses of the assessments. As a result, a school cannot devote time or effort to topics that are extraneous to the Common Core, including topics in discrete mathematics. Why was discrete mathematics not included in the Common Core? In my article, I give three important reasons for this phenomenon. First, instead of writing standards that would prepare students for college, careers, and citizenship as originally intended, the goal of the writing group was shifted to prepare students for calculus. In other words, the standards were hijacked. Of course, this assertion will be denied by the authors and advocates of the standards. At this point, it is appropriate for me to note that I am not opposed to having standards in mathematics. Indeed, I played a leading role in the organization, creation, and adoption of high mathematics standards for New Jersey in 1996, 20 years ago, and again in 2002. Standards which certainly played a role in New Jersey's consistently high performance on the National Assessment of Educational Progress. Standards are, I believe, very important, but these standards should be applied to and be appropriate for all students. Not all students need to take calculus. Not all students need to be able to find 64 to the 2/3 power. And not all students need to manipulate algebraic fractions, a skill that is only useful in calculus. Many topics in discrete mathematics are more valuable for all students than the topics needed to succeed in calculus. Many topics in discrete mathematics are more accessible to all students than the intense algebra needed for calculus. Many topics in discrete mathematics can demonstrate to all students how mathematics is applied in today's world. And many topics in discrete mathematics provide opportunities for all students to learn about mathematical reasoning and problem solving. A second motivation behind the calculus focus of the core curriculum was the belief that the U.S. needs more students who are preparing themselves for STEM careers. STEM is an acronym for science, technology, engineering, and mathematics. And the belief that the way to increase the STEM pipeline is to ensure that more students take calculus in secondary school. Our research shows that the opposite may be true. That is, many students who take calculus in high school, and in particular advanced placement calculus, do not continue to STEM careers. Students exit the STEM pipeline for a number of reasons. Some because they were inadequately prepared for and therefore performed poorly in pre-calculus and calculus courses, and some simply because of lack of encouragement towards STEM careers. Others were only virtually in the STEM pipeline. That is, they took advanced math and science courses only because doing so enhanced their ability to get into the colleges of their choice. Thus, it is not that the STEM pipeline is too small, but rather it is too leaky. Too many students exit the STEM pipeline. The solution to this problem should be retaining students who are already in the STEM pipeline, rather than recruiting more students into the pipeline, except for students in mathematically impoverished schools. A third reason for deleting discrete mathematics from the curriculum is concern about the scores of U.S. students on international assessments, which are based on the curriculum that is common to all of the participating countries. Countries that have a broader curriculum are at a disadvantage because if their students spend only 90% of the time on the common topics, they will not do as well as students from countries where 100% of the time is spent on those topics. Therefore, if increasing scores is important, and the obstacle to higher scores is the curriculum, it follows that we should narrow the curriculum so that our curriculum is as narrow as possible. Thus, discrete mathematics has to be deleted. Unfortunately, instead of facilitating a broadening of the mathematics curriculum, the international assessments seem to have the opposite effect, at least in the US. To summarize all three areas of concern, the focus on preparation for calculus, the desire to expand the STEM pipeline, and the concerns about international assessments all seem to support the conclusion that discrete mathematics is not important. And in each of those three areas of concern, I believe that this conclusion is not justified. Ultimately, the U.S. will recognize that not all students should be preparing for calculus, that the STEM pipeline does not have to be expanded if its leaks are controlled, and that our scores on international assessments are neither significant nor important. And once those mistakes are recognized, discrete mathematics will be allowed to, and indeed will be invited to, re-enter the U.S. math curriculum. When will that happen? I don't know, but I believe that it will happen. And I am acting on that belief by continuing to work on improving my textbook, a preliminary edition of which I am now holding. This textbook, entitled Reasoning and Problem Solving with Discrete Mathematics, which has an important focus on reasoning and problem solving, is primarily intended for a course for secondary students, but is also currently used in college courses for prospective middle school teachers of mathematics. The book is described in the materials that will be distributed shortly and on the book's website. Both include a table of contents, a history of the book, and a representative sample of the over 400 pages in the book. Unfortunately, I can't sell you this copy by passing it through cyberspace, but you can order a copy of the book through the website. I would like to focus on an important theme that occurs in the book, the theme of systematic reasoning. This theme arises in a number of contexts, so the book speaks about systematic coloring, systematic counting, systematic listing, systematic constructing, etc. I will talk about several examples. Keep in mind that the content information in these examples may not be very significant, but that the experience that students have with learning how to use systematic reasoning can be very significant in shaping their thinking in mathematics and in other areas of human endeavor. One class of problems for which systematic reasoning is critical consists of those problems that begin with the phrase, find all. For example, if you give young children cut-out shirts and trousers of several different colors and ask them to find all outfits that can be made, they will typically proceed in a random fashion. When they show you all the outfits they have made, you will find that some outfits are omitted and some are duplicated. Discrete mathematics provides a way of learning to answer such questions systematically. First, by constructing a chart where the shirts are listed at the top and the trousers at the left, and the outfits can be found in the boxes. Then by using a tree diagram, where the first branching is for the shirts, and the second branching is for the trousers, and ultimately by using the multiplication principle of counting, which in this context says that if there are 4 ways of selecting a shirt, and in each case there are 3 ways of selecting trousers, independently of which shirt is selected, then there are 4 times 3, or 12 ways of selecting both. That is, there are 12 outfits altogether. Note that the tree diagram also provides a way of systematically listing the 12 outfits. If you follow each of the branches of the tree, you end up with the vertical list of all 12 outfits on the right. Similarly, if you ask secondary students to find all factors of 200, they will most likely proceed randomly. The same strategies presented above can also be used in this situation. Since any factor of 200 is a product of a power of 2, from 0 to 3, that's 4 possibilities, and a power of 5, from 0 to 2, that's 3 possibilities. So 200 has 4 times 3, or 12 factors. Thus, students can arrive at a systematic way of finding and of listing all the factors of 200, and can see that this problem is the same as the previous problem of finding all the outfits. In learning how to solve both problems, the focus is moving from random behavior to systematic behavior. Here's another find all example. Find all graphs that have exactly 4 vertices. Rather than proceed randomly, students can learn to break a difficult problem into cases, a problem-solving strategy that might be called divide and conquer. This is not an obvious strategy. Students have to learn when and how it can be used. In this example, the cases might involve the number of edges that the graph has, and the students might solve the problem by constructing all 4 vertex graphs with no edges, then all 4 vertex graphs with 1 edge, then all 4 vertex graphs with 2 edges, and so on. The solution to the initial problem is then obtained using the addition principle of counting, which says that if you split the items to be counted into groups, then the total number of items is the sum of the numbers of items in each group. How many different graphs are there with 4 vertices? The addition principle of counting says that the answer is the number of 4 vertex graphs with 0 edges, plus the number of 4 vertex graphs with 1 edge, and so on, up to the number of 4 vertex graphs with 6 edges. Thus, the total number of different graphs with 4 vertices is 11. Wait a minute, you or your students might exclaim. Aren't there 6 different 4 vertex graphs with 1 edge? Doesn't the fact that each edge connects 2 different vertices make these 6 graphs different? This is an important question. When are 2 graphs the same, and when are they different? And this question is an example of a perennial question in mathematics. When are 2 objects the same, and when are they different? For example, when are 2 numbers the same? Although the 2 numbers in each pair look very different, students come to learn that they are actually the same, that is, equal. Many are never able to reconcile themselves to the fact that 0.99999, etc. is equal to 1. When are 2 triangles the same? The first 2 are recognizably the same, even at a young age. But it takes a while before children recognize that the third triangle is the same as the second, and probably even longer to recognize that the fourth is the same as the third, and even longer to recognize that the fifth is the same as the fourth. Eventually, they understand that if they can reposition a shape so that it matches another shape, then the 2 shapes are the same, in which case they are referred to as congruent. The same principle is used in dealing with graphs. If one graph can be repositioned so that it matches another graph, then the two graphs are the same. They are referred to as isomorphic. Thus, the 6 4-vertex graphs with one edge are all isomorphic, since each graph can be repositioned so that it matches each of the other graphs. Wait a minute, you or your students might exclaim. Can't you get another 4-vertex graph with 5 edges besides the one we had before? The one we had before is on the left. A new one is on the right. These two graphs certainly look different, but you can transform the new one into the old one. Just reposition its top right vertex and the edges adjacent to it so that it is located below its bottom right vertex, and you'll see the old graph at the left. As an exercise, systematically determine how many different two regular graphs there are with 15 vertices. What is a two regular graph? That's a graph where each vertex has degree 2. What's the degree of a vertex? The number of edges that meet at the vertex. First, convince yourself that any two regular graph must be a collection of cycles. The problem of finding all different graphs with 4 vertices is one example of systematic construction. Another kind of example is to find all different graphs with 5 vertices, of which 2 have degree 3 and 3 have degree 2. How do you even begin to solve this problem? Again, you have to think systematically. You know that there is a vertex of degree 3, so you draw one vertex, call it A, and link it to 3 other vertices, B, C, and D. Drawing this part of a graph is not an obvious first step. Students have to learn to convert verbal information into graphic form. Now you know there is another vertex of degree 3. Where is it? It could be E, in which case, since E has degree 3, it must connect to B, C, and D, the only vertices that have room for another link. And now look, we have found a graph with the desired properties, 2 vertices of degree 3 and 3 of degree 2. But the second vertex of degree 3 could also be one of the vertices B, C, or D in the graph at the top left. Let's suppose that it's C. Then we need to connect C to 2 other vertices. If we connect C to B and D, as in the graph at the top right, then there are no vertices to which E can be connected, although it must have degree 2. So connecting C to B and D doesn't work. We have to connect C to E and one of B and D. Let's connect it to B, as in the graph at the bottom left. Finally, we connect D to E, since those are the only 2 vertices which have empty slots for an edge. When we do that, we find that we have a second graph with the desired properties, 2 vertices of degree 3 and 3 of degree 2. Are there any other graphs with these properties? For example, if instead of selecting C to have degree 3, we had selected B to have degree 3, perhaps we would have found a third graph with these properties. In fact, it can be proved that there are no other graphs that have 2 vertices of degree 3 and 3 vertices of degree 2. Wait a minute, isn't it possible that these 2 graphs are also isomorphic? After all, they both have the same number of vertices of each degree. However, when we look at these 2 graphs side by side, we see that they are different. One way they are different is that the graph on the right has 3 vertices that form a triangle, but there is no triangle in the graph on the left. That makes it impossible for the 2 graphs to be isomorphic. No matter how we move the vertices of the second graph, those 3 vertices will still form a triangle. The net result is that we have systematically constructed all graphs with 2 vertices of degree 3 and 3 vertices of degree 2. There are exactly 2 of them. As an exercise, you might try to construct systematically all different graphs with 2 vertices of degree 3 and 4 vertices of degree 2, or all different graphs with 2 vertices of degree 3 and 5 vertices of degree 2, etc. If you want a real challenge, try constructing systematically all graphs with 8 vertices, all of degree 3. As a final find-all example of systematic reasoning, let us consider the question of how many different dishes containing 3 scoops of ice cream you can make if 8 flavors are available. Your immediate response might be 8 choose 3, since there are that many ways of selecting 3 out of the 8 flavors. But that would only be correct if the problem stated that the 3 scoops have different flavors. It doesn't. Or your immediate response might be 8 times 8 times 8, which would be correct if we were counting the number of ice cream cones. Since a cone that has chocolate, then vanilla, then strawberry is certainly different than a cone that has strawberry, then chocolate, then vanilla. But with a dish of 3 scoops, the order of the scoops doesn't matter. How do you solve this counting problem, where order doesn't matter and repetition is allowed? You have to consider several cases, solve each using the multiplication principle of counting, and then add the results together using the addition principle of counting. A student who has learned to solve this problem has mastered several different techniques of mathematical reasoning and problem solving. In this problem, all 3 scoops could be different, in which case there actually are 8 choose 3 or 56 possibilities. Or all 3 scoops could be the same, in which case there are 8 possibilities, since there are 8 flavors. Or there could be 2 of one flavor, 8 choices there, and 1 of another flavor, 7 choices there, another 56 possibilities. So adding these all together, we get a total of 120 possible ice cream dishes. As an exercise, determine how many different dishes there are with 4 scoops of ice cream, where there are 8 flavors, and where 2 dishes are the same if they have the same number of scoops of each flavor. As noted earlier, although the content information in these examples may not be very significant, the experience that students have with learning how to use systematic reasoning to solve problems like this, which have no prerequisites beyond elementary algebra, can be very significant in shaping their thinking in mathematics and in other areas of human endeavor. However, they need to start having these experiences in the early grades, as was recommended in the discrete math portion of New Jersey's math standards, and that are appropriate for students in all countries. These recommendations are presented in detail in my article for the ICME 13 volume. They include 2 topics of discrete mathematics that were recommended by the National Council of Teachers of Mathematics in 1989 as appropriate for all grades: systematic listing and counting, and vertex edge graphs, and that were developed more fully in NCTM's Navigations books on discrete mathematics. Systematic listing and counting is essential preparation for probability. It involves sorting and classifying in the early grades, organizing information in grades 3 through 5, and using the multiplication principle of counting in the middle grades. Essentially, all of this is missing from the national standards, which evidently assumes that all students will be able to absorb these topics as they learn probability in high school. Not a good assumption, since probability is the trickiest of all math topics. The study of vertex edge graphs enables students to discuss and solve a variety of modern applied problems involving networks, such as efficient routes for snowplows or delivery trucks. This topic is also valuable, as we have seen, because it provides an accessible arena for students to focus on problem solving and reasoning in an interesting context. The study of vertex edge graphs also introduces the important modern topic of algorithms. For example, one that, given a street map, will help generate an efficient route from A to B. At early grade levels, the study of algorithms involves following and later devising instructions and developing theoretical and developing strategic thinking skills. This topic, like systematic counting, had been included in New Jersey's math standards since 1996, but is entirely absent from the national standards. These discrete math topics are more valuable to all students than much of the material that is geared only toward those who are calculus bound. And I sincerely hope that in the coming years these topics will once again have the prominence in the school curriculum that they deserve and that our students deserve. Thank you very much for your attention.